So I'm going to base it on the Green Book, and I'll follow roughly the same sequence as the Green Book, so you can follow it and revise it at home. So, what is the point of navigation? Why do we spend so much time on the ground school of doing the nav? Because we all know that we can just look at a map and we can just see where we're going. Well, the reason why we have to put so much work into navigation is, unlike a car, we can't stop. Once you're in the air, time just continues moving. There is no option to slow down and start thinking about navigation. And we have to fly the plane. We aviate, navigate, communicate. So you'll find that unless you've got the trip very thoroughly planned in your own head and you've got that plug in front of you, that you can't fly the plane and navigate at the same time. So this whole course is all about how to fill in that plug and how to use the plug. So now nav is divided into two subjects, navigation and flight planning and performance. Now, there's a huge overlap between navigation and flight planning and performance. And I cover an awful lot of flight planning performance in this navigation. So we were talking about maybe delaying nav. Well, delaying nav can be very useful because what I can do is to slot navigation in with flight planning and performance, because the two subjects are very, very similar. So let's push on with navigation. So here's the planet. Here's one I prepared earlier. So let's start off with the very, very basic 10-year-old geography. So what actually is Vinny, what's a day?
Day is full rotation of the Earth.
A full rotation of the Earth. And Danny, what is a year?
A full orbit around the sun.
Complete orbit of the Earth around the sun. So the Earth is going around the sun, and as it's going around the sun, the Earth is rotating, and of course the Moon is going round the Earth. It takes about 28 days to go round the Earth. So lots of things all rotating around one another. And what determines whether it's spring, summer, autumn or winter is, as the Earth is going round the sun, it's tilted. You can see the Earth has a tilt. So as it's rotating, it's not rotating exactly in line with the sun, it's tilted. And so it's going round the sun like this. And because the tilt stays the same, what essentially is happening is that it, as far as the Earth is concerned, it looks like it's tilted through a different angle as it goes from summer to winter. So how much it tilts by is we call the Tropic of Cancer and the Tropic of Capricorn. So the Tropic of Cancer is a line extending around the Earth here, north of the equator, and what that is, that's defined as the most northerly point where the Earth manages to get directly in line with the sun. So we call that the Tropic of Cancer. And then the Tropic of Capricorn is the same thing that's south of the equator. That's that once again is when the sun is directly overhead. So what do we find? What is the equator then, Robbie?
Center of the Earth.
The center of the Earth.
Well, the longitudinal center of the Earth.
Yes, that's probably good enough to answer the exam question on it.
The widest point of the Earth.
Yeah. So in other words, it's if we imagine the Earth is spinning around, yeah, it's the perpendicular circle that goes all the way around the Earth to the axis of rotation, isn't it? Is how we define the equator. So there's the equator, and then of course we've got the Tropic of Cancer, Tropic of Capricorn. And the point the Earth spins around is called is
it the poles?
Yeah, so that's the North Pole and the South Pole. So in other words, that's true north and true south. Now that's not where compasses point. We're going to talk about that a bit later on, but that's the point the Earth actually spins around. As it's spinning around, we've talked about the two tropics. You can probably see that if this was tilted towards the sun, as it's rotating, if the North Pole is rotating rotating towards the sun, then as you go round the other side of the North Pole, it's still actually exposed to the sun. So that means that as we go through the seasons, there must be a point on the Earth where the North Pole has a day and a night. And we call that the Arctic Circle and the Antarctic Circle. So the Arctic Circle is where anywhere within the Arctic Circle, there's at least one day a year where the sun never sets. And of course, one day when it never rises. So these are our 5 lines: Arctic Circle, Tropic of Cancer, Equator, Tropic of Capricorn, Antarctic Circle. And sometimes there's an exam question on all of that. So let's look at latitude and longitude. So we've said that the Earth spins around true north, and the Earth is divided into lines of latitude and longitude. So lines of latitude are basically 0 at the north, at the equator, and then they go all the way up to 90. So if all this point here on the Earth, about 45 degrees, this will be 45 degrees north. This will be north, and this will be 45 degrees south, and this will be 90 north, 90 degrees south. But how far up here is the line of latitude? It is just simply up up and down in degrees, starting at 0 to 90 north to 90 south. And then lines of longitude are then lines, once again, they go from true north to true south, and they're just a line that's drawn around the Earth, going from true north to true south. Now, because England ruled the waves, and the British astronomers were much cleverer than the stupid Portuguese, French, and Spanish astronomers, the line, the 0 degrees line of longitude goes through Greenwich, through the Greenwich Observatory, in fact. And if you go to the Greenwich Observatory, and actually go, you can actually go and see the original telescope that they charted the planet from, and drawn on the ground, there's like a white line with a piece of brass that's set into it that defines 0 degrees, and it actually aligns exactly with the telescope optical system. So that's where 0 degrees comes from. It was measured to the Greenwich Observatory, and then lines of longitude extend east, so they extend all the way around the Earth to 180 degrees east, and they extend all the way west from the Greenwich Observatory all the way to 180 degrees west. So the first significant thing you should notice is that latitude goes 0 to 90 and longitude goes 0 to 180. So that means there's 3 digits in longitude and only 2 digits in latitude. And that's actually how you tell the two apart. One's got 3 digits, one's got 2 digits in it. What the early sailors did is they wanted a way of measuring distance. So we've got lines of longitude, and these are going in degrees, 0 to 90. And they divided the lines of longitude, each degree, into minutes. And there was 60 minutes in 1 degree. And they've said that 1 minute equals 1 nautical mile. So that's the definition of the original definition of a nautical mile was 1 minute of latitude. So if I said to you, how many miles is it from the North Pole to the South Pole? What do you reckon? How would you calculate that, Vinny?
Using the degrees, it's 180.
180 multiplied by 180 times what?
I'm having a complete brain fart.
I won't edit out this bit, you know. It's going to go to the whole club. So the whole club's going to be taking the piss because Vinny said there's 180 miles from the North Pole to the South Pole. That means you could walk it in a day.
No, it's got to be timed by 1,000.
Any advance on times by 1,000? Phone a friend. What do you reckon, Danny?
No, it's not 1,000.
What is it then? Well,
I've got
It's
nothing.
100.
how many
100.
nautical miles? How many minutes?
Is
are
it
there?
60?
What is a
60.
nautical mile? There's a nautical mile is 1 minute. And
Yes,
60.
60.
so Vinny was dead right. There's 180 degrees from north to south. So it's 180 times 60 is a distance from there to there in nautical miles. Yeah.
Yeah.
Mhm. Now, that brings us nicely to the fact that that's actually what we call a great circle. So a great circle is a circle that runs all the way round the Earth. In other words, its circumference is equal to the all the way round. So any line of longitude, any longitude that's drawn on a chart will be a great circle. So what do you reckon, Robbie, about lines of latitude? Are they great circles? It's a trick question, by the way.
Oh, I was going to say yes.
One of them is. So remember, lines of latitude go all the way around the Earth like this, don't they? So the line of latitude that's the equator is a great circle because it goes all the way around the Earth, doesn't it? It's the maximum size it can be. A great circle is the maximum size going along the surface of the Earth. But if you think about all the other lines of latitude, they go around like this, don't they? So they're not great circles. They're what's called small circles because they are smaller and smaller in diameter as we get nearer and nearer the North or South Pole. So any line of latitude is a great circle, and lines of latitude only are great circles at the equator. Now, in the early ships, of course, they actually had a globe sitting in the captain's office, a beautiful, great big wooden globe that had all these things, had all the countries and things marked on them. But of course, yeah, we want to fly a plane, don't we? You know, and we want to drive a car, and we want to do this, don't we? We want to put that on our lap. We can't stick a globe on a back seat. So what we have to do is we have to convert a globe into a map. So how the crap do we take? How do we take this and make that into a sheet of paper? Well, that's always been the issue. So what you could do is we could just make a globe like this of the Earth, maybe stick a light bulb in the middle of it like this, and maybe we could put a sheet of paper kind of around the Earth like this, and we could then project the countries and things onto a sheet of paper. You know, maybe we could use a bit of photographic paper, project the globe onto a sheet of paper, and then what we take away would be a copy of the globe. And that's basically what a map projection basically is. But can you see there's a small issue now in that if I just put a bulb in my globe and put a sheet of paper here, that this isn't going to be a true representation of the globe, is it? Because the lines are going to produce errors, aren't they? In other words, it's only going to be a really good representation when the paper is in contact with the globe, isn't it? As soon as I'm moving it away, you know, it's going to be up the creek. In fact, you can probably see on this one that if my sheet of paper was up here, I mean, this little bit of the Arctic would be projected over a huge, great big distance. So all of the distances on the projection are all going to be up the creek. Well, that's a fat lot of good if we want to use it for navigation. So we call this a projection. Now there's two different sorts of project. Now there's many ways of projecting or making a map. Now the ones we use in aviation is what's called a Lambert conformal and a transverse Mercator. So so let's just look at a transverse Mercator. I can pull up a nice little presentation of that. Save me trying to draw something that's circular on the board. So you can see basically what's happened is you put a light bulb in the middle of the globe and you've wrapped a sheet of paper around it, and then what's happened is that we've unrolled the sheet of paper, and that's our map. But what actually happens is that it's going to be quite good here, but as we get right up here, you can see that for a very small bit here, a distance here is going to represent a huge distance on the map. So that means that it's not going to be very accurate, and of course it's going to be distorted. And this is like a typical example of how a piece of the Earth would, how a piece of the Earth would actually be distorted, how the lines of latitude and longitude are going to come out. Now, of course, we don't actually need to put this piece of paper vertically. I mean, let's say, for example, we just wanted a map of England or a map of the UK. I mean, we could probably find a better way of putting this bit of paper around the Earth. I mean, we could put it on the skew so that, for example, the bit of paper was directly in contact with Birmingham, so that we'd get a much better, a more accurate projection. So that's a Mercator projection where we just roll a column of paper around the Earth. Now there is another type of projection, and that's called a Lambert's conformal projection. And a Lambert's conformal projection looks a bit like this. So what we do is we put a same concept. We could put a bulb in the middle of the Earth, but this time we wrap a cone of paper over this globe, and then we just unwrap the cone. As you can see, it looks like this. Now, the great thing about the Lambert's conformal projection is that it represents distances better. It doesn't distort the distances quite as bad. But you can probably see from this diagram here that the straight lines, the lines of longitude and latitude, aren't straight anymore, they're bent. But the great thing is that the distances that it's representing are much, much more accurate, even though the lines of latitude and longitude are a bit more pissed. Compared to, say, a Mercator projection that we just talked about, where we've on a Mercator projection, generally the lines of longitude and latitude remain straight, but the distances are way off. So generally for aviation, most of the things is Lambert's conformal. So what's the difference between a map and a chart? Well, a map is just a projection of the surface of the Earth. A chart has other things added to them that might be useful, that aren't necessarily, that might not even be on the physical things on the surface. So what do I mean by physical things on the surface? Well, they may not actually in reality exist. A typical example would be airspace, where we have different classes of airspace marked. So even if we take a satellite picture of the Earth and we can, on a computer, we can very accurately make that into a map, it won't show the airspace because that's something completely different. So a chart has all this extra information on over and above a map. And what we use for aviation is what's called a topographical chart. So a topographical chart means it has topography shown on it. In other words, it's got the hills represented on it. So although it's a two-dimensional sheet of paper, we find a way of representing heights on that two-dimensional sheet of paper. And we also add all of the extra bits and pieces as well. So charts all have a scale, and typically a scale will be something like 1 to 500,000. Now that means that 1 centimeter on the chart represents 500,000 centimeters in reality. So obviously 500,000 centimeters is 100 centimeters in a meter. So that represents 5,000 meters, or 5 kilometers. So the first thing we need to talk about then is have you guys got your CRP on you? Your whiz wheel? Well done. You're doing better than the instructor because he tidied his away earlier on. What the shit did I do with it? I'm sure I put it in this bag. There we go. Yeah, sorry. Aha. I told you I tidied it away. Look, I put it in its proper little case. I wasn't looking for it in its case. So let's start talking about the CRP computer and what it does. Right, so if you can start by just putting the inner and the outer scale together, so the 10's over the 10, the 11's over the 11, the 12's over the 12. In other words, it's just a it's just not doing anything. What this is an old-fashioned slide rule, but it's been made into a circular slide rule, and it multiplies and divides for us. Now, if you look carefully around the outer scale, can you see it says kilometers, meters, liters, yards, imperial gallons, US gallons, feet, nautical miles, statute miles? Can you see it's got all those things written around the edge? Yeah. So what we can do is we can use this to convert from any units to anything. So let's just find out, for example, I want to convert 1 yard into feet. So the first thing we do, if we want to convert 1 yard into feet, you take a guess the answer. So I reckon I don't know, let's say there's probably going to be, I don't know exactly how many feet are in a yard, but a yard and a foot is slightly smaller than a yard. So let's say that there's going to be 2 or 3. So we take a guess at the answer. Now, what we do is you put on the outer scale, can you see you've got this bit you can move round? So just put your cursor on yards. And then under where it says yards, put 1. Now you haven't got 1, so just put 10. So can you see what I've done there? Is I've got yards, and underneath it, I've put the cursor on it, and I've put 10 underneath it, which is 1. Now look round all the way round until you find the bit that says feet, and then move the cursor all the way round to the point it says feet. And then look what it says underneath the feet, and tell me what figure you get underneath feet. Shout it out. What do you get?
3.
Well, it actually says 30, doesn't it?
Well, 30, yeah.
Yeah. So now we know that we've guessed the answer between 2 and 4. So we know that it's not 30. We know it's not 0.3. It's got to be 3. So let's keep going. So what we're saying is how many feet are in 1 yard? Well, we've just found out that's 3. So move it round to meters, because I want to know how many meters there are in a yard. So just whiz it round to where it says the cursor, find the bit that says kilometers, meters, and liters. And tell me what's underneath it. What do you get?
It's 9.
It's 9 point. What do you get?
9.1.
I
Oh, you're perfectly laughing
9.2.
here.
9.2.
I've got absolutely no idea what I'm looking at, Paul.
Right, so can you see what I've done is I've moved the cursor around to where it says meters, where it says M for meters.
Yeah.
Danny, you gotta start with 10 under yards.
Yeah, so yes, you've got to start with putting 1 yard. Yeah. So you've got to put 10 under yards, just like that. Yeah.
Okay.
So find yards and put 1 underneath it. Now we can't. Now 1 is actually 10. So it doesn't matter if you put 10. You're putting multiples of 10. This doesn't do the decimal points. You have to do that in your head. So start off with 1 yard. Yep. Have you done that?
Yeah.
Right. And then find out how many feet that is by moving the cursor all the way. Keep don't move the slide rule, don't move the whiz wheel, and just move the cursor around to feet. And tell me what it says under feet.
Yeah, I've got 30 there now.
Right, now just move it a little bit to where it says kilometers, meters and liters.
Yeah.
And then tell me what you've got underneath kilometers, meters and liters.
9.1.
Yeah, sort of 9.1, 9.2, something like that. So so that means that in 1 yard, how many meters are there in 1 yard? Well, let's have a think. Well, a meter is about the same as a yard, isn't it? Roughly. So that means that we want about 1 yard, and that's about 0.92, 0.915, something like that. So we know the answer is going to be 0.9. So this is basically how we're going to convert from one unit to another unit. Now, in the exam, you'll get questions on this. There's always a question on chart scales. Now, the question will take the form, and it will say something like, let's put a typical example in. On a 1 to 500,000 chart, in other words, a half mil chart, what distance does, say, a 1 foot represent in nautical miles? So that's a typical question. So now the way you would do this is that in fact, let's make it slightly harder. Let's make it what distance does 1 inch represent in nautical miles? Right, that's a typical question that you're going to get in the exam. So you'll notice that we've got a scale, we've got inches, and we want the answer in nautical miles. Well, what you could do is in the exam, you'll be given a calculator. So what you can do is we can convert this into another unit that we can convert on our whiz wheel. So we know that 1 inch is 500,000 inches, isn't it? So we know we've got 500,000 inches. But that's not really a lot of good to us, is it? Unless we know how many inches there are in a nautical mile off the top of our head, we aren't going to be able to solve that. So if somebody could divide 500,000 by 12 for us, what's the answer for that? If you've got to count on your calculator or on your phone.
41,666.6667.
Right, so what is it? 41,666.
1,666.
So in other words, we know that so that's how many feet it is, yeah? Now we want to convert 41,000, roughly 42,000 feet into nautical miles. So let's take a guess at the answer. So if we've got a half mil chart and 1 inch of distance, the answer is probably going to be what, 2 or 3 miles, would you say? Don't know, 2 nautical miles, 3 nautical miles, something like that. So what we can do is we can use our whiz wheel to actually come up with the answer. So what we do is we find feet. There we go. So I found the feet, and I'm going to put 41667 as best as I can. So I've got 41 So I reckon that's about, on my one, that's about there we go, 41667 under feet. So I put 41,667 feet under feet. Best I can. And then what we do then is once you've done that, you can move the cursor around until you find the bit that says nautical miles. And on my one, I've got about 6.8 nautical miles, 6.9 nautical miles, something like that, underneath nautical miles. Now the answer, now in the exam, they might not be quite so, they might say 1 in 5,000, what distance does 1 inch represent? They might not say in nautical miles. They might, for example, say, they might give you the answers as 6.8 nautical miles might be A. B might be 15 kilometers. C might be 4 statute miles, and D might be 12 statute miles, for example. So that would be typical 4 answers. And you're going to, so I'll show you how we would actually get that. So we've already calculated that it's going to be probably 6.8 nautical miles is probably, I would say, our hottest guess so far. So how many kilometers is that? Well, let's say, for example, nautical mile kilometers, about twice as much roughly. So what you would do is you would now move the cursor around to the point where it says kilometers. And tell me what it reads under kilometers. What do you get for kilometers?
12.9.
Yeah. So it's so now you'll notice you don't have to move the whiz wheel. All you're doing is moving the cursor. So that's about so we know that it's going to be about 12.9 kilometers. So we could probably go right, let's work out how many statute miles it is. So now, once again, don't move the wheel, just move the cursor around to where it says stat M for statute miles, and tell me how many statute miles it is. What do you get for statute miles? What do you get in there, Danny?
I'm lost, Paul. I'm not gonna lie.
Okay, so where we started off, we were trying to convert 42,000 feet, and the way we do that is, do you remember when we started? We put, you see where it says feet, yeah,
Yeah.
right. Under, you put your cursor onto feet, and under feet you've got
When you say cursor, you mean the red bit,
yeah, the red bit, yeah.
not the line, the actual inside wheel. Is the cursor.
No, you put the red, you put here the red line, yeah. The red cursor you put onto feet, yeah.
Yeah.
Yep. And then underneath then you move the whiz reel around like this, yeah.
Yeah.
And so the inside wheel is reading 41,667. 41,667. So in other words, you're trying to line up 41.6. Yeah. And that will look like that. So you've now moved the inner scale to align 41.6. Yeah. Now, what you do next is you don't move the inner scale to the outer scale. What you do is you just move the cursor. So we know that that's feet, and it's 41,000 feet. So if we want to know how many nautical miles that is, what we do is we rotate this round until we find nautical miles, which I've lost it. It's here. Yeah, there we go. So you find nautical miles.
Yeah.
And then you put the cursor up onto nautical miles. Yep. So you put that on the nautical miles arrow like that. Yep.
Yeah.
And then read off what it says on the inside. And what do you get?
It's like 6.85.
How much?
6.85.
What are you on?
I think you're on statutory miles, Paul.
Yeah, I fucked it all up, haven't I? Sorry, guys. I'm trying to read it backwards. Yeah, there we go. Yeah, so you're dead right. So yep. So well done. I got it wrong. You got it right. 6.8, about 6.85 nautical miles. Now, because we don't know, this won't tell me if we're dealing with 0.68 nautical miles, 6.8 nautical miles, 68 nautical miles, or 68 million nautical miles. It doesn't actually tell us that, does it? All it's telling us that it's 6.8. So you have to guess the answer and know what the answer is going to be before you can use this. So you've got to know roughly within reason what it's going to be. So I know that the answer is 6.8 nautical miles because it's not going to be 68 and it's not going to be 0.6. And then exactly the same thing is if we want to get the answer in kilometers, we've already moved the inner and the outer scale so that we've already got 41,667 aligned. So all we have to do is to convert it to kilometers is just move the cursor onto the bit that says kilometers. And what do you get and what do you get there, Danny, under kilometers?
So that's like 12.7.
Yeah, about 12 point whatever that is, 12.6, is it? 12.7, 12.7?
Yeah, that's 12.7.
Yeah, 12.7. And then once again, for statute miles, if you just find statute miles around the top where it says stat M's, how many statute miles is that? What do you get as the answer for that?
7.85.
Yeah. So it's going to, yeah, it's about right. So, and we know that it's 7.85 statute miles. So that means that, yeah, this is the answer.
Paul, so the question, why did you pick, when it says what's the distance in inches or in 1 inch or percent? Did you just go for 12 inches in a foot because that's convenient on the wheel?
Okay, why did I go for 6.8 and not 68 or 68 million or 0.0068? Right.
No, that's not my question.
Oh, wasn't it?
No. Why did you choose the relationship between inches and feet? Couldn't you, if you're asking me, could you have picked anything? If all it takes is the inner wheel and matching up the pieces, could you have picked the relationship of yards? Or
I most certainly could have
meters?
done. I could have converted. Well, let's do it, shall we? So let's just calculate this differently. So we know that we've got 500,000 inches. So can somebody on a calculator divide that by 36 for me, please?
$13,888.
13,888.
88.8, so 89 really.
That's more than my was. We're all okay. So now that's yards, now, isn't it? So that's yards. So we've got to convert 13,888 yards into nautical miles. So what we do is if you find yards and put your cursor on yards and then put 138. Well, that's 30. That's more or less. That's as best as I can manage. That's 13.9. So if you put sort of 13.9 less an atcock under yards, okay, and then read off and then find nautical miles and tell me how many nautical miles that comes out to be.
Yeah, it's the same.
I mean, what's happened is the inner and the outer scale are exactly where we put them to start with, aren't they? And of course, that's not much of a coincidence, really, because if we looked round and found feet, well, next to feet is 41667. So chances are that you can probably see that one of the secrets to these scale questions is that it's quite handy to have something in as many things as you got in your head as you can memorize, the better. So if you know that there's 3 feet in a yard, there's 36 inches in a yard, and if you know that, for example, off the top of your head, that there's how many inches there are, or how many feet there are in a nautical mile or a statute mile. It doesn't matter what you've memorized, but the more and more you can memorize, the easier the exam question will be, because you can probably get a lot closer on your first guess. So let's talk a little bit more about scale. What I want to do is to bring up
I assume when we're not allowed our like nav rulers in the exam, are we?
no, but you are allowed your whiz wheel, and they will give you a calculator. So so this is a typical chart. So what we're going to do is we're going to have a look. I'm going to navigate round this chart together, and this is a chart of the UK. So let's start by looking around the edge of this chart. So what I want to do is I want to look right at the very bottom of this chart. Let's just move the camera and the bit a little bit around. Right, so here we go. Right, what's the first thing you notice in the very bottom left-hand corner? It's got scale 1 to 500,000. So this is a typical aviation chart, and it's called a half-mil chart. Now you'll notice that on the chart, you've got here nautical miles, statute miles in kilometers. We've got this as a little scale here, haven't we? So that means if I measured any distance on this chart, I could probably just get my dividers, put it on a distance, and I could then put my dividers down the bottom here, and it would give me the distance in either kilometers, nautical miles, or statute miles without going through all this performance. How else could I measure distance on this chart, do you reckon? Well, let's have a look. Can you see we've got lines of latitude and lines of longitude running across the chart? So here is the 50 degrees north line of latitude. So do you know, the first thing you notice is that this 50 degrees north line of latitude isn't straight, it's actually slightly curved, isn't it? So what projection do you think this chart is? Do you think it's a Mercator projection, or do you think it's a Lambert conformal projection?
Lambert.
It's a Lambert conformal projection because the Lambert conformal projections, the distances are pretty good, but the but of course it distorts the latitude and longitude. So let's have a quick look down here. I'm looking for the bit that says Lambert's conformal. It's got it written on the chart here somewhere. Maybe it's in this corner. So it's got lots of useful information. It doesn't have, somewhere on here, it tells me what the projection is, and it tells me the exact point in latitude and longitude where the projection is actually made from. But that information is contained on this chart.
Mine says it directly under the scale in the middle. So it's got scale 1 to 500,000, and then it's got Lambert conformal conic projection standard parallels. Right down the very bottom.
Let's have a look. Oh yes, well done. Good spotting. Yep, so right down the bottom of the chart, yep, it says Lambert conformal conic projection standard parallels 4920 and 5440. Convergence, in other words, so it's telling us the exact spot the cone was placed over, and it's telling us the angle the cone was made. In other words, you know, how extreme a cone it was used, and it's telling me that the datum was WGS 84. Now, what it means by the datum WGS 84, that's where the North Pole actually is. In other words, in 1984, that's where they decided the North Pole exists. That's where somebody said, this is where the North Pole is, guys. And all charts now are made to WGS 84. Right, so we've talked about we can find distance here. What's another way we could find distance on the chart, do you reckon? We're going to talk about lots of different ways we can find distance. So let's have a look, shall we? So we've already said that this is, we've got 50 degrees north is here. So if we look up the right-hand side here, can you see it's got 50 degrees north and we've got 51 degrees north. So what's the distance between there and there in nautical miles?
60.
60 nautical miles, because it's 60 minutes. So we know that the distance between here and here is 60 nautical miles. So if you look, we've got these big tick marks, haven't we? So we've got 10, 20, 30, 40, 50, 60. So that means that this one here is obviously a line of a line that's obviously a half a degree. That's 30 minutes up. That means that each one of these ticks here, each is going to be 1 nautical mile, 1 minute. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10, 20, 30, 40, 50, 60. So that means these lines of latitude here, this is obviously 50 and a half. Now, if there's the 60 minutes, that means this line of latitude is 50 degrees 30 minutes north. Yep. This line that runs all the way along here. In other words, it's 50 degrees and it's 50. That we know that's 10 minutes, that's 20 minutes, that's 30 minutes. So that means this line here is 30 minutes. So we can measure the distances, can't we? Because we could take a pair of dividers between any 2 points, and then I could put the dividers up on any of these vertical lines here, and I could physically measure the minutes, and that would tell me how many nautical miles it is on the chart. So that's another way we could measure distance on the chart, isn't it? How else could we measure distance? Well, somebody mentioned we could use a scale ruler. So now we know the scale of this chart is 500,000, isn't it? So now if you look at this scale ruler, can you see that it's got 2 scales on it? One that says 1 to 250,000. And then on the other side of the ruler, it says 1 to 500,000. And because it says 1 to 500,000, we can actually measure off the distance in nautical miles directly using our ruler. Obviously, we've got to make sure we've got the right scale, but we could just put this on the chart, couldn't we? And we could actually just measure off the distance in nautical miles directly. So we've got 3 ways of measuring nautical miles. And most of these other, these little protractors and all these other little tools, for example, you see this one here says, this is a simple protractor, says 1 to 500,000. And you can actually see that I could actually just read straight off here, couldn't I? I could just measure it using this little instrument here as well. So we can normally measure it off our protractor, we can measure it off our ruler, we can measure it off in minutes, or we can just look at the bottom of the chart. So there's many different ways of measuring nautical miles. So we talked about the fact that this is a chart. So and this is a topographical chart. And Vinny, what did I mean by a topographical chart?
Is that the way that it's been projected onto?
No, that's the projection. And a projection gives you a map. So what's the difference between a map and a chart?
So it's obviously got things that you may not physically see, like airspaces and
chart. And a topographical chart means what we're trying to do is we try to put 3-dimensional information on the chart as well. So let's start by looking at this 3-dimensional information actually on the chart, shall we? So how do we represent 3-dimensional information? Well, we represent it in contour lines. So we see here we've got elevations in feet. So you can see that the color changes to shades of brown, representing different heights. And we've also got these contour lines, and it's showing, it says here, contours are shown at intervals of 500 feet, AMSL, above mean sea level. So everything on this chart is above mean sea level. So let's just find somewhere on the chart to have a look at, shall we? Somewhere that's not too crowded. We can have a look at the oh, we can't look at the Brecon beacons anymore, can we? So we can look at the which is probably what they've called the Brecon beacons now. But this is the Brecon beacon. So let's have a look at the what we can see. Well, first off, you can see we've got these numbers. These are called spot heights. So these are showing you the height above mean sea level for the tops of each of the various hills. And you'll notice how the colour changes as we go up the hills. And can you see we've got these lines here on the chart? Can you see you've got, if I just zoom right in on over here, that's a great thing about Zoom and things. I can actually bring these right up in great detail. So this is a contour line. So everywhere on this line here, that's 1,000 foot above sea level. Everywhere along this line here, this contour line is 1,500 feet above sea level. So this is 1,000 foot. This is 1,500 foot above sea level, this brown bit here. And the very top of this hill is 1,932 feet above mean sea level. So obviously the height here in the sea is 0. Of course, it won't be 0 in reality because of the tides and all sorts of things. But yeah, as far as we're concerned, aviation-wise, it is. Now, you'll notice as well that where we talked about the lines of longitude and lines of latitude, that it nicely divides this whole chart into squares, doesn't it? Can you see how we've got like a square here, we've got a square here, we've got this is a square, yeah? So it's divided it all into these rectangles. And in the middle of each rectangle, there is a number. So this number in this rectangle, for example, is 2 with a little 5 next to it. Now we call these MEFs, maximum elevation figures. And this is the highest point above mean sea level of anything within that square. So that means this whole big square here, the tallest thing on this chart is 2,500 feet. So let's just zoom in and see what that probably is. So here's that big square, and we know that the highest, the maximum elevation within here is 2,500 feet. Well, look, we've got a hill here that is just beyond that square. It's 2,566. So what it's saying is that just here within this square, the maximum is 2,500 feet. That probably means that this square above it is going to be something much bigger, and you'll see that it is. This square above has got 3,900 is the maximum elevation figure of the square above it. And this one to the right is 3,800. So why is that useful to us? Well, if you're flying around, obviously flying into mountains will not make your day. So as a quick guide, you can look at the maximum elevation figures of the chart as a thing to know what is the height within any one square anywhere in the UK, what the maximum elevation figure is. So that will give you a pretty good idea the lowest height that you can sensibly fly at. Now, of course, that's not necessarily to say that you must fly higher than that. That's just the maximum sort of a good starter for 10 that you would use for the purposes of your navigation. Now, there are exam questions that says, what does the MEF figure actually mean? And it is the highest above mean sea level of that square. Now, of course, that doesn't mean that you can't, for example, here, let's look at this 2.5. So if we were flying from, let's say, I don't know how to pronounce that, Pweli or whatever it's called. If we're flying from this place, Pweli, all the way down to, let's say we're going to Aberystwyth, and we were going from there to Aberystwyth, although the maximum elevation figure is 2,500 feet, you could probably see that I could fly from there to Aberystwyth quite safely at 1,000 foot if I wanted to. So they're not necessarily the minimum height that you can fly at. They're just, it's just a rough guide, you know. So that's the MEF. So what else do we have on this chart? Let's have a look at a few things, shall we? So we've talked about how heights are shown. Let's look at a few other things, heights, shall we? And a few other bits of information. Well, right, okay, well, there's London. Well, we don't go anywhere near London if we're sensible in an aircraft. But coming out of London, for example, you'll notice that we've got the M4 motorway is marked here. So the M4 motorway is going all the way down here, put through, skirts round the bottom of Reading, carries on round here, and the M4 motorway heads us all the way out here, and gets to Membury here, and heads us off to Swindon. So why on an aviation chart will we show the M4? I mean, what on earth use is that to us? What do you reckon, guys? Why are we going to show the M4?
And it's to help us sort of navigate as a landmark to refer to.
Well, absolutely. The M4 is a great big motorway that's huge that you can see from miles away. And it's very, very distinctive in the UK. And it runs east-west. And you can see it from like 20, 30 miles away. It's huge. So it's a very, very useful point of reference for navigation. So what is shown on this chart are all of the useful things that we can navigate from. So what other things have we typically got that we can use to navigate? Well, you see Reading's marked here as a great big yellow splodge. Yep. And Reading is huge, isn't it? As is like Basingstoke. Let's look at what else we've got, shall we? So if we were flying along here, what do you think we would notice if I was flying along, flying west, and I was flying with the M4 on my left? I'd fly over the top of Reading, and I'd be flying here with the M4 on my left. What do you think I would see when I was getting roughly to here at Hampstead Norris, straight ahead of me?
Got the A34 going northbound, so roads go north.
Yeah, obviously, you're dead right. I would see this road that's heading north south.
Change of the ground as well.
But can you see that we've got all these hills here, haven't we? Coming up ahead. So as I was flying along here, I'd see all these big hills in front of me, wouldn't I? And how high are these hills? If I wanted to follow the M4 over the top of these hills, how high are the hills? What gives you a clue?
they're not high because the maximum elevation for that box is 1,300 in the first two boxes.
So not that big a hill, but what would actually tell me how high the hills are?
The actual contour lines, so you can see the 965, 950,
Yeah, they're not.
974.
Yeah, they're not contour lines, are they?
Oh,
They're
sorry, the
heights.
spot heights. I said.
So we'd look at the spot heights. Yeah. So we know that these hills are 910 feet high there, 965 feet there. When I say 965 feet, this spot height, what's that height above? What is that relative to?
A horse.
Relative to the horse. Relative to a horse in the field. Yeah, right. So what happens if the horse is in the barn? So what is this height relative to, guys? When I see a 965
Sea level.
sea level, yes. So that means that the hills are 965 feet above mean sea level. Now, also you'll notice that following the M4, we've got something here at Membry. So there's a service station at Membry. This is Membry Services, and you'll notice that at Membry there's this triangle with a thing on the top. Now this is a symbol on the chart, meaning that there's a mast at Membry. So every mast has got two numbers against it. So this bit here means the mast has lights on the top, and the big number is how high the top of the mast is above mean sea level. And the figure underneath it is how high it is above the ground. So in other words, this mast is 504 foot high, and the very top of it is 1,191 feet above mean sea level, above the sea. So you could probably work out how high the hills are if you subtracted those two numbers together, subtracted one from the other. That would give you the approximate height of, would give you the height of this area around, wouldn't it? How high the hills are. In other words, it's a 500-foot mast placed on hills that's about 600 feet above sea level, with the top of the mast being 1,190 feet above sea level. So they're the masts shown as those little shapes there, and these circles are airfields. So we've got a circle with a cross in it is a disused airfield. So what the crap use is it to us to show a disused airfield, to show Welford that's disused?
Could be a good emergency diversion if you weren't going to make it to the other airfield.
Yeah, now be careful that you don't select that answer in the exam. It's a disused airfield is a good diversionary airfield. Needless to say, the exam question will show that as one of the answers, and that is the wrong answer. So somebody else come up with a good guess for me. Why on earth are we going to show disused airfields on a chart? I'll give you a clue. I fancy flying to Furze Farm Airfield. Why would I want to show Welford, the disused airfield, on the chart? What on earth use is it to me? What do you reckon? Any guesses?
It's then you don't land at the wrong airfield.
Absolutely. So you don't land at the wrong airfield, because if I want to fly here and I was following the M4 and I got to here, I would probably go, there we go. I can see an airfield, what looks like an airfield. Yeah, a great big thing, like a couple of buildings. It looks like that's the runway. That's where I'm going. But the fact that I've shown it as disused means that if I was flying to here, I know that just next to First Farm, there's Welford, which is a disused airfield, is just down the road. And in actual fact, Welford is quite a distinctive, very prominent place in the UK. And First Farm is a piddly little nothingness. And in fact, if you didn't have that marked, you'd almost certainly want to head to you'd finish up at the wrong place. So airfields are marked on the chart. So here's another famous one, Greenham Common. Obviously highly controversial, now closed, but was highly controversial back in the Cold War days. Lots of American activity going on in Greenham Common. So what other sort of things have we got marked on the chart? So what do you reckon, guys, this blue, we've got the M4 marked in red, this big motorway here, and we've obviously got other dual carriageways and roads marked. What about this big blue thing that's wiggling around the chart? What's that?
Oh, I got it. It's a river.
It's the River Thames. Yes, it's a river. So rivers are also marked, rivers and canals, because they're a very good landmark for us to follow. So we're getting quite a few things that we could probably navigate from. We've got motorways, we've got rivers, we've got big towns, we've got masts shown. We could probably find all of those, couldn't we? We've got disused airfields. So if we're flying north, for example, let's start at White Waltham Airfield here, and we flew north here. We could probably find Henley, because we know Henley is on the River Thames. So if I just flew out of White Waltham here, I could probably find this big town here, and I could probably find this bend in the river here. So I could probably fly to this bend here because I know that Henley is just off to my left. If I got a bit confused and flew to here and flew to Marlow, and Marlow and Henley are very similar, I could say, well, hang about, whoa, is the river running north-south, or is the river running east-west? And by looking at the two, I could probably guess whether I was at Henley or Marlow. So lots of nice things that we could find on the chart. So what other things are marked on the chart that we've got to look at? Right, let's look at something else that we might be able to navigate from. Right, here we go. I'll show you one bit on the chart that your instructor ballsed up. I recently had to revalidate my my commercial license, and I did a nice balls up, in that you see this black line here, right? What do you think that could be? You see, it's got like a dash here. It's got little dashes on it as it goes, as it is. So what do you reckon that black line is?
Power lines?
Not a bad guess.
Oh, train lines.
Is it a rail line?
Yeah, it's a railway track. Now, as I discovered on my navigational exercise, I found a nice railway track that I And I thought, oh, that's a bit strange. Obviously, I must be getting lost because I didn't find it shown. In actual fact, I found the new HS2 line that's not shown on the chart. I thought, great, that's like all I needed. So what else have we got here? So what's this? What's this here? There we go, right in the middle of the chart. What's that? That triangle? Tell me what that is, guys. North of Oxford.
Matt,
Mast.
Yes, a mast. How high is the mast above ground?
553 foot.
Yeah, 553 feet, and it's 999.3 feet above sea level. And just to the north of the mast, there's a giant duck. What does the giant duck mean?
Potential bird activity.
Warning, one ducks half a mile long exist in here from the prehistoric days. So how, oh, hang on, what's happened to my chart? Oh, what happened to my chart? Oh. Right, let me just go back to my chart. Here we go. Right, so what we could do is let's just find out what that duck is. So we haven't a clue what it is. So at the bottom of the chart, there's a range of symbols. So now I'm sure that there isn't such a thing as really a duck that exists that's going to be a mile big. So what we could do, we could look all in the bottom of these here for all the symbols, and there is actually a duck in a circle here, and you can see what it says. It says bird sanctuaries, and it says pilots are requested to avoid these portions of airspace during the periods detailed in the UK AIP ENR 5.6. So you see there's all of these symbols are shown on the chart. So in other words, what it's saying is you don't really want to chop up all the ducks, and you don't really want to suck them into your engine either. So this is showing you and all of these various symbols are at the bottom of the chart. They're showing you lots of things. Right, let's look at something else, shall we? So let's look at the danger areas and things, and that will probably be here we go. So let's find something nice, shall we? A danger area I'm familiar with, or a dodgy area I'm familiar with. Here we go. Okay, so can you see we've got these circles, and they've got lines that go through them? Well, these are either restricted or prohibited areas. So this is showing you here, we've got a restricted area. Its number is 101 and it's restricted up to 2,400 feet. And this is 104, also restricted up to 2,400 feet. So this is the restricted areas of Aldermaston and Tadley, and of course, being military guys, you'll know exactly what goes on at Aldermaston and Tadley. And needless to say, the military like to keep light aircraft away from Aldermaston and Tadley. So this is a typical example of restricted area. Now, you can actually find out a bit more about the restricted areas. You see it says R101, for example, at Tadley. So what I could do is I could actually find 101 on the chart. Oh, will you stop doing that? Ah. This is right, let me just nasty thing right, so let me just do that again for you. Right, so if we so 10 right, so 101 is what we're looking for. So if I just go down to the bottom of the chart, can you see there's a something here that tells me what every single restricted area actually is. So I can look here for all these danger areas and restricted areas, and it's got a list of them at the bottom of the chart, and basically what you're allowed and not allowed to do with them. Now, the difference between restricted and danger is the restricted area is restricted all the time. Now, a danger area may be a danger one day, and it might not be dangerous the next day. And some of the restricted areas are also restricted for different types of restrictions. So, for example, it says here, restricted areas 107, 264, 212 only apply to helicopters. Seems a bit strange. Why do you think that, Robbie? Why would you have restricted areas just for helicopters and not for aeroplanes?
Either the air blast can blow the blades, or because the helicopter can hover and just stay in one spot.
What sort of restricted areas do you think they are if they're restricted to helicopters? Give a think. What would you not want helicopters near?
Power lines?
No, open prisons?
My second guess.
So generally, these are restricted areas because they're prisons. They don't mind aeroplanes flying over them, and be my guest to land in one of them. But helicopters, they don't like helicopters landing in prisons. So let's find a danger area, shall we? And then we'll right. Let me see if I can find a danger area. So let's just think of a nice danger area, shall we? So that's a power station. That's a nuclear power station. That's restricted because it's there all the time. So there's a few danger areas here on the south coast. There's quite a few I know near. Here we go. Right, here's a nice danger area here. So can you see this purple area here? Yep. Doink. And it's got this lines here. And this is a danger area. And it's danger area and it's number 9A. So danger area 9A. So could I fly in that danger area 9A? Could I take my airplane and fly it there? Well, how are we going to find out? Now, it does say here that Plymouth Military West lower aerodrome radar service. So that means that and it's got a frequency here. So we could call them up and we could say, can I penetrate danger area 9A? And there's always a telephone service where you can call up, you get pre-recorded message, and you can get this off the internet as well. And it will tell you what danger areas are active at any one time. And if I wasn't sure, I could look up danger area D009. So let's just go to the bottom here and find D009. So here we go. So that tells me here that danger area D009 is controlled by Plymouth Operations and it's got a phone number here. So what I could do is rather than fly all the way there and discover I can't fly there, I could actually give Plymouth Ops a ring before I set off in my planning stage, couldn't I? And I could ring that telephone number and say, I want to penetrate danger area 009A. Can I do it? And they would say, oh yes, it's not active this week at all, and do what you like. And so we can fly through danger areas. We can't fly through restricted areas. Well, we might be able to, but the actual area will be restricted up to a certain height. Now there are some peculiar restricted areas. I'll show you some really weird ones that's unique to here we go. Right, here's a danger area. It says danger area 124 stroke UNL. What do you think UNL means? Take a guess. UNL. What do you reckon, Danny? What does UNL mean? So UNL means unlimited. It has unlimited height. So what on earth do you think goes on in danger area 124 that its height is unlimited? Well, that's the testing ground of top secret laser weapons that shoot satellites out the sky. So that's why it's unlimited, because even 50 miles up, it's still firing a laser up into space. So that's where the British American test their laser weapons. There's only one of those in Europe, to my knowledge, that says UNL on it. So we can get lots and lots of different information from this chart. So what I'd like to stop there, and then what I'm going to do is tomorrow. Well, I'll find out what everyone else wants to do, but the next thing we want to do is we need to talk about navigational marks, navigational assistance marks on the chart, and these are all of these sort of things like you see these where we've got these frequencies and things and bits and pieces, the VORs, the DMEs, the ADFs, and the non-directional beacons, and all that sort of gear. But let's call it quits there, and I think it's beer time.
Sounds good to me.
All right, now I'll put on the WhatsApp message what everyone wants us to do. If we want to delay nav, or we want to carry on, or whatever, and we'll get some feedback and work out what Paul wants to do tomorrow. Yep.
That's great.
Thanks, Paul.
Okay, guys. So thanks for coming, and we'll find out what happens next. Okay. Cheers.
Brilliant. Thanks a lot, Paul.
Okay.